For today's lesson, we are going to continue our coverage of 8.1. So in our last lesson, we introduced the notion of what it meant to be equinumerous. So two sets are equinumerous if and only if there is a bijection between the two sets. We also introduced the notion of countable. A set is countable if it is finite or if it is equinumerous to the positive integers. But along the way, we also saw that the positive integers is equinumerous to the integers themselves. So another way of saying that a set is countable is to say that it is equinumerous to the integers. For today's lesson, we are going to investigate further countable sets, their properties, and along the way, we're going to prove that the rational numbers are countable. And so that's the goal for today. So let's go ahead and get started. So we're going to start off with theorem 815. And so what this says is, suppose A is a set. And we want to prove that the following three statements are equivalent. A is countable. Either A is empty, or there is a function from the positive integers to A that is onto. And lastly, the third statement, that there is a function from A to the positive integers that is 1 to 1. So let's go ahead and prove this. So let's go ahead and do 1 implies 2. So suppose that A is countable. Well, if A is countable, we have by definition that A is finite or is denumerable. So then A is finite or denumerable. Now, we're going to proceed by cases. And so the first case, let's go ahead and call this case 1. We're going to suppose that A is finite. Then, by definition, we have that if A is finite, then it's going to be equinumerous to some I sub n for some n, for some natural number n. Then A is equinumerous to I sub n for some natural number n. Now, from here, we do have the possibility that n is equal to 0. If n is equal to 0, then I sub 0 is equal to the empty set, and thus A is empty, which concludes this situation since we already have the either A is empty. Which concludes the case for n equals 0. So suppose that I sub n, so suppose that n is a positive integer. Now, we know that in is equinumerous to A. So by definition, there is a bijective function g going from I sub n to A. And now what we are going to do is construct a function that is onto the positive, from the positive integers to I sub n. So now, define h to be the function going from the positive integers to I sub n by h of x is going to map to x if x is less than or equal to n, and it's going to just map to 1 if x is greater than n. So what am I doing here? We know that I sub n is going to be the set of numbers less than or equal to n. And so this is going to look like 1, 2, 3, and then we're just going to go all the way until we get to n. So that's the set I sub n. So what we are doing here is defining a function from the positive integers, but we are constructing it so that it's onto. Because now we have that, once we have our input x, this is mapped to x if x is less than or equal to n. But we are looking at all the positive integers. So if x is equal to 1, we map to 1. If x is equal to n, then we map to n. And then finally, if x is greater than n, then we are just going to map to 1. But that gives us a function that is onto. So by construction, h is onto. But now, the fact that h is onto and the fact that g is a bijective function tells us that by theorem 525 that the composition of the two functions is going to be onto. Because if we have f and g onto functions, their composition is onto. And so let's go ahead. So by theorem 525, the composition, where we have g composed h, when this is going to be what we're defining f, so f is equal to g composed h, which is a function going from the positive integers to a, is onto. And that takes care of case 1. And so now we have our onto function. So let's proceed and do now case 2, where a is infinite, but specifically it's the numerable. So suppose that a is the numerable. Well, if a is the numerable, that means that the positive integers is equinumerous to a, and thus there is a function, a bijective function. So here we're using the definition of what it means to be equinumerous. F from the positive integers to a. And that finishes it off for 1 implies 2. Now we're going to do 2 implies 3. And so we have two assumptions here. We have a is empty, or there is a onto function from the positive integers onto a. So let's go ahead and do this. So first suppose a is empty, the empty set. Then f from a to the positive integers is the empty set. And so here, what I mean is when we view the function f as a relation, if we go back to chapter 4, when we first define relations, keep in mind all functions are relations. That is that the function is really a subset of the Cartesian product of a with the positive integers. But a is the empty set. And whenever we have the empty set Cartesian product any set, that's going to be the empty set. And so this is telling us that f is the empty set. So now, with that in mind, we get back that f, since f is actually the empty set, that this is going to be vacuously 1-to-1. And so f is going to be a 1-to-1 function since we have no element to choose from. For the conditional f of a equals f of b implies A is equal to B. And so it does 1 to 1. And so that takes care of the case when A is the empty set. We have now found our 1-to-1 function just because there's just the one function, namely the empty set. So now let's go ahead and suppose that A is non-empty and assume the existence of this function that is onto. So now suppose that A is non-empty and that there is a function, an onto function. And I'm going to switch the notation. So here we have f, but over here in 3 we want to also show f. So what I'm going to do is change this symbol to a g, and we want to show that there is a function f that is 1 to 1. And so there is an onto function g from the positive integers to a. Now what I'm going to do is take a step back and discuss the intuition for what we are about to do. To motivate what we are about to do, let us go ahead and take A to be the set of the positive even integers. And let's go ahead and define G from the positive integers to the even integers by G of n, where G of n is defined piecewise. It's going to equal 2n if n is odd, and it will be n if n is even. So what we see is that if we plug in 1, we get back 2. But if we plug in 2, we get back 2 as well. But now at 3, we're going to get 6. But at 4, it's just going to get back 4. And all the even integers, 6 goes to 6, 8 goes to 8. And all the odd ones get doubled. This g is going to be an onto function. And we see that every even integer is going to get hit, because we have that this is being mapped to, every even integer is being mapped to itself. So we will have this is onto. But for the purposes of the proof that we are just looking at, what we want to prove is the existence of a function f from a to the positive integers that is 1 to 1. In the context of this example, we want to construct a function from the even integers to the positive integers, so that this is 1 to 1, but we want to use it, construct this function, assuming this g that we have here, because that's all that we have to work with in our proof. So how can we go about constructing a function that is 1 to 1? Well, the first thing is we need to send every even integer to exactly one positive integer. So let's go through. We have 2. We can send this back to 2, but we could also send it to 1. And that's what we are going to do. We're going to map 2 to 1. And the key thing is, even though we have that 2 is being mapped to by 1 and 2 under G, we're choosing the least positive integer that maps to 2. And so the least positive integer mapping to 2 is 1. Then we get to the next positive integer, positive even integer, 4. So we go to 4. And so we look at our set of outputs and we ask, which is the least n that maps to 4? And in this case, it's going to be 4 itself. So we're going to map 4 to 4. Then we get to the next even integer, 6. And so at 6, we want to ask, what is the least positive integer n that maps to 6? And so we see that the answer here is 3. And so we go and map 6 to 3. 8 only appears over here, so that's just going to be 8. And finally, for 10, it will be 5, since 5 is the least n that maps to 10. And then we continue in this manner. And so we can see here that for 12, this is going to correspond to 12 itself. And then 14 will correspond to 7. So in other words, f of n, if we wanted to rewrite this in terms of g, in terms of these least value, we want to say that this is the least n, so the minimum, in the set of positive integers n, such that, oh, let me switch this to m, such that g of m maps to n. And so that's what this is getting at in abstraction. Just to showcase this in a concrete sense, what this notation means, we're taking f of 2, this here is the set of m's in the positive integers such that g of m is equal to 2. And so now this here is going to be the set of 1 and 2, since both of those map to 2. And we just choose 1. Now the minimum, we have a way of interpreting that in terms of a function, because the low ordering principle guarantees to us if we have a subset of the natural numbers that is non-empty, it has a least element. So we know that there will be a least element in f of n. And so let's go ahead and define this now in the proof itself. So we're going to go ahead and define. So next, so for a, in a, we have that the inverse image of a, which by definition is those elements in the positive integers such that g of m is equal to a, is non-empty, since g is onto. And so we have that for every a in a, g inverse of the inverse image of the set containing a under G is going to be non-empty, since this set is a subset of the natural numbers. We have that there is a least element. And G inverse, set containing A, which we denote by the minimum of G inverse, the set containing A. So now, define f going from the positive integers, from A to the positive integers by f of A is mapped to the minimum of G inverse set containing A, and so the inverse image, the minimal element, which we are guaranteed by the ordering principle. And I just noticed that while I said it out loud, I did not write it down. And so this here is by the ordering principle, that existence of the least element. And so we have our definition for f of A. Now observe that if we take G of f of A, we get G of the minimum of the inverse image of A. But now the inverse image of A is the set of all those positive integers m that map to A, and we're taking the smallest value of those, and then once we have that smallest value, it's some positive integer that maps to A. So that G of that is going to be back A. for each a and a. So we have this equality. And thus, we have that g composed f is the identity function on a. And now we have theorem 533 to the rescue, which tells us that if we have a function g from b to a, such that g composed f is the identity, then f is 1 to 1. And so by theorem 533, f is 1 to 1. And that takes care of 2 implies 3. And all that remains is to show 3 implies 1. Okay, so let's go ahead and show 3 implies 1. So we're supposing that there is a 1-to-1 function f from a to the positive integers. And now we're going to construct a new function. So now define g from a to f of a. So in other words, the range of a under the function f by g of a is mapped to f of a. So all that we are doing is changing the set of outputs from the positive integers to the range. So note, as a reminder, image of a, this is the set of f of a, and a. In other words, the range of f, which is going to be a subset of the positive integers. So with that, so we have our function g, then g is going to be onto. Then g is onto by construction and g is 1 to 1 since f is. Consequently, g is a bijective function and thus we have that a is equinumerous to f of a. So now we're going to quote a theorem that we're going to prove in the next slide. And that theorem tells us that if a is a subset of the positive integers, then a is countable. And so since f of a is a subset of the positive integers, we have by theorem 1 that f of a is countable, and thus a is countable since a is equinumerous to f of a. And that finishes the proof. And so all that remains is to prove this statement right here, which we do now. So let us go ahead and now prove the theorem we just quoted. And in fact, this theorem is essentially the same argument that is given in the proof in the text for 3 implies 1. The only reason I have isolated it is that by thinking about it from this point of view, we are going to be able to give simpler arguments to some of the results in the textbook pertaining to whether the Cartesian product of the natural numbers of itself is countable, are the rational numbers countable, and so we're going to be quoting this result to ease in the presentation of proving these statements. And so that's the reason why I have gone ahead and isolated this theorem, even though it really is the statement 3 implies 1 in disguise. So let's prove this. So we have a is a subset of the positive integers. So if a is finite, so if a is finite, then a is countable. So suppose A is a subset of the positive integers such that A is infinite. So it suffices to show that A is the numerable. Okay, so let's go ahead and continue. Since A is non-empty, and A is a subset of the positive integers, we have, by the Wall ordering principle, that there is a least element. And let's go ahead and denote that least element A sub 1 of A. And so we have our least element A sub 1. Now, define A sub n recursively, technically A sub n in A, recursively as the least element of A minus A1, A2, all the way through A sub n minus 1. For n greater than or equal to 2. So what does this mean? Well, A sub 2 is defined as the least element of A minus A1. Because now if we plug in 2, we have 2 minus 1, so just 1. So we're just doing A minus 1. So A sub 2 is the least element. Let me just put that in here, just to keep this in here. A2 least element of A minus A1. Then A sub 3 would be the least element of A minus A1, A2. And then we just continue in this manner recursively. Note that the A sub n's exists by the Wall ordering principle. Since A minus A1 and A sub n minus 1 is non-empty and is a subset of the positive integers. And so now that we have these elements A sub 1, A sub 2, A sub 3, so on and so forth defined, now we can construct a function. So next, let f be the function that goes from the positive integers to A, and we're defining this. F of n goes to A sub n. So we claim that f is a bijection. So let's go ahead and show this. So let us start off with 1 to 1, and as an aside, to show that something is 1 to 1, we have two approaches we can take. So we could take f of A is equal to f of B, and show that this implies that A is equal to B, or the contrapositive of that. A does not equal B, and then that implies that f of A does not equal f of B. To show 1 to 1 here, I'm going to show this implication. Okay, so let's go ahead. So suppose that n and m are positive integers such that n does not equal m. Well, if n does not equal m, we have two possibilities. N is less than m, or n is greater than m. And so here's where we can use this phrase, without loss of generality, that we've introduced in the past. And so we can assume, since both cases will be the same, we can assume one case. And so without loss of generality, we may assume that n is strictly less than m. Well, in this case, we have that a sub m is going to be an element of a minus a1, a2, all the way through a sub n m minus 1. And so now, as a consequence, we have that because n is less than m, thus a sub n is not in this set. And so we have that a sub n is not in here, and hence f of n is not equal to f of m, which shows that f is injective, that is 1-to-1. And so we have injectivity. So now we're going to go ahead and show that f is surjective. So next, and so to show that it's surjective, we want to choose an arbitrary element of a and find a positive integer that maps to it. And so we're going to choose some arbitrary element of a. But now a is a subset of the positive integer, so lowercase a is a positive integer. So then there exists a k in the positive integers such that a is the least element of a minus a1, a2, all the way through a sub k minus 1. And so here what we're doing is asserting the existence of some positive integer k, such that if we remove all the elements that are strictly less than a, and we're assuming that there's k minus 1 of them, so we remove each of them, then we can guarantee ourselves to have a as the least element of this set. So consequently, we have that f of k is equal to a, which shows that f is onto, and thus bijective. So therefore, since f is bijective, we get that a is equinumerous to the positive integers, which shows that a is numerable, and thus countable. And that finishes it off for the proof. So we are done. And with this result, we can now prove some statements that the book does explicitly in a very nice and quick way. Let's go ahead and do that. So now let us go ahead and use the theorem we just proved to show that the Cartesian product of the integers with itself is countable. Now in the text, this is done, and the way it does it is by constructing this function f, where f is a function going from the Cartesian product of the positive integers with itself back to the positive integers, and it's defined in this way. But in order to show that the Cartesian product of the integers with itself is denumerable, you have to prove that this function here is both 1-to-1 and onto. But even then, you have to also deduce that this is the for the function that you want. And that requires a clever deduction, because the way that this function is attained is by looking at the following pattern, where we want to map the point 1, 1 to the positive integer 1. So in red, I'm going to be denoting the outputs of this function in this grid. And so we have that 1 there. And then we're going to have that 1, 2 is going to map to 2. And so this is going to map to 2. And then 2, 1 is going to map to 3. And then we continue. 1, 3 is going to map to 4. And what we have is that we are essentially going in this direction. We're going 1, then 2, 3, then we come back up here, 4, 5, 6. Then we're going to come back up and do 7. And then this here will go to 7. This here will go to 8, 9, and 10, and we'll continue. 11, so on and so forth. And that's what's being depicted here. And so we have this function f, which is illustrating this ability of us being able to count every single element in the Cartesian product of the positive integers of itself, hence the name countable, because we're counting all the points. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, so on and so forth. So we can count every element on here. But of course, in order to show it's countable, by definition, we need to exhibit a function and then prove that it's both 1 to 1 and on to the positive integers, which at times is difficult because we need to be able to construct such a function. This theorem, however, allows us to bypass this, because what we could do instead is show a function that is 1 to 1 towards the positive integers. So we're going to prove the corollary, but the way we're going to do this is via the following. So we're going to construct a function g from the positive integers Cartesian product to its here to the positive integers. So just as before, like this. So we're doing this again. But here's the difference, such that g is 1 to 1. We are not going to prove that it's onto. We're going to rely on this theorem to conclude that it's onto. To conclude the countable part. So let's see how we do this. So here's the proof. So let g be from the positive integers Cartesian product, positive integers to itself, to the positive integers, be defined by g of the ordered pair a comma b maps to 2 to the 8th power times 3 to the bth power. That's our function. Completely different to this, doesn't require any clever manipulation. We are just sending this to 2 to the a times 3 to the b. We claim this is 1 to 1. So we claim that g is 1 to 1. So to do this, we're going to consider two different ordered pairs such that we have equality. So suppose that g of a comma b is equal to g of a prime comma b prime. So in particular, we have 2 to the a, 3 to the b is equal to 2 to the a prime, 3 to the b prime. Now, we know that a and b and a prime are positive integers, and either they're equal or one is going to be greater than the other. And so without loss of generality, we may assume that a is less than or equal to a prime. Now, by having this, we can now divide. Then, we get 3 to the b is equal to 2 to the a prime, 3 to the b prime, over 2 to the a, but exponent rules allows us to rewrite this as 2 to the a prime minus a, 3 to the b prime. Note that a less than or equal to a prime is equivalent to a prime minus a greater than or equal to 0. So this here is an integer. Since 3 to the b is odd, it must be the case that a prime minus a is equal to 0. Because if it were not, we would have that this here will be some positive integer. But if it were some positive integer, then we have that 2 times this quantity is going to be, this is going to be an even quantity, this is odd, and we know that that's a problem since an integer can either be even or odd, but not both. So it must be the case that a prime minus a is equal to 0, so this is, which is equivalent to a prime being equal to a. And thus, we get 3 to the b is equal to 3 to the b prime, and which implies that b is equal to b prime. Therefore, a comma b is equal to a prime comma b prime, which shows that g is 1 to 1. Or in other words, it is injective. Now, we're going to redefine g. So next, let f be the function defined from the positive integers Cartesian product itself to the image of g. So g of the positive integers Cartesian product itself be defined by f of the order pair a comma b is just simply g of a comma b. And then g is onto by construction. So we've constructed it so that it's onto. We have put the whole image of g, in other words the whole range of g, as the definition of this function f, which is defined in terms of g. And so now f is going to be onto, oops, typo, that's f. So f is onto by construction, and it is 1 to 1 since g is. Thus, f is a bijection and therefore we get that the Cartesian product of the integers with itself is equinumerous to the image of the g, the image of the positive integers with itself under g. But g of the Cartesian product of the integers of itself, the positive integers of itself, is now a subset of the positive integers by the theorem above we have that G of positive integers, Cartesian product with itself, is countable, and thus A is countable. Oops, not A. Positive integers with itself, Cartesian product is countable. And so we're done. And so as a recap, we have a subset of the positive integers. The theorem tells us that then this is countable. Any subset of the positive integers is countable. So we get that this is countable. But if this is countable, and the fact that we had that f was constructed to be a bijection tells us that if this is countable, and since it is equinumerous to the Cartesian product of the positive integers with itself, then we end up concluding that the Cartesian product of the positive integers with itself is also countable. And so that finishes it off for this proof. Now, I've gone ahead and isolated this theorem, but notice that in reality, this is the statement for the theorem that we proved. From 3 implies 1. Because what this 3 is telling us is that if we have a function from a set A to the positive integers that is 1 to 1, then A is countable. And that's exactly what we have here. We didn't have to refer to the theorem, to this theorem about subsets. We could have just referred to the previous theorem and concluded it. Because what we have constructed initially is a function g that is 1 to 1. And so since this function g is 1 to 1, the theorem allows us to finish the proof immediately after proving that it is 1 to 1. So let's go ahead and rewrite this proof and just conclude it from that theorem. The reason I isolated this result here is just to emphasize the inner mechanics of why that theorem holds, is that really we're saying inside the proof we have a subset of the positive integers, ergo the set is countable. So here we are, back to the corollary. If we had gone through the same exact proof, and once we proved that g is a 1-to-1 function, since we have a function from a set, namely here, Cartesian product of the positive integers of itself to the positive integers, and we have shown that that function g is 1 to 1, now we get from 3 implies 1, since these are equivalent, by theorem 815, we do get that the Cartesian product of the positive integers of itself is countable. And so let's go ahead. So by theorem, so therefore, we take the Cartesian product of the positive integers with itself is countable by theorem 815. And so we're done. And so that's the benefit of these results, is that we bypass having to find a function that is actually bijective onto the positive integers, as is the case with how the book proceeds about it. And we can now just prove it directly from the theorem, once we show that there is some 1-to-1 function going towards the positive integers. So the next result is the following theorem. The rational numbers is the numerable. And so in other words, the rational numbers are countable. Seeing this, why this is the case, is actually not that bad. Because we can imagine that we can list all the rational numbers in the following way. We can have 1 over 1, so we have 1. Now let's go ahead and do 1/2. We have 1/3, 1/4, 1/5, so on and so forth, going in that direction. Over here we have 2 over 1. Then we're going to have 2 over 2, 1 again. Now we're going to have 2 over 3. And then we just continue in this manner, 2 over 5. And then over here we have 3 over 1, 3 over 2, 3 over 3. until we have this grid of rational numbers. And then we can see that the fact that the rational numbers is countable is a consequence that we can essentially count them. So we want to construct a function from the rational numbers to the positive integers where we send this element to 1, and then we go like this. In the same way that we did for the Cartesian product of the positive integers with itself. We come along like this. Oops, there we go. And then we just count along this function. But that requires that we need to be to some degree clever if we wanted to construct a function that was one-to-one and onto the set of the positive integers. But with the theorem that we have just proven recently, all that we need to do is find a function from the rational numbers to the positive integers that is one-to-one. But we are actually going to break it down into some intermediary steps and then use the properties of equinumerosity, the fact that it is transitive, to conclude that the rational numbers is denumerable. So let's go ahead and get started. So here's the proof. So we're going to let f be a function, not from the rational numbers, but from the positive rational numbers, to the Cartesian product of the positive integers with itself. So we're going to let this function be defined by f of a over b is equal to a comma b, where a comma b in the positive rational numbers is chosen so that a and b have no common factors. Now this is crucial because when we take the elements, say 1/2 and 2/4, they are the same rational number. And so we want to have that input goes to the same output. And so by restricting to only those rational numbers that are in simplest form, we can guarantee that this f is a function. Okay, so continuing on till we have this a comma b. So we're going to claim that this function is one-to-one. So we claim that f is one-to-one. So to see this, we're going to go ahead and take two rational numbers. So suppose f of a over b is equal to f of c over d. Then we end up getting that the ordered pair a comma b is equal to the ordered pair c comma d, which is equivalent to a is equal to c and b is equal to d, and thus a over b is equal to c over d, which shows that f is injective. Now, by the previous corollary, we have that these positive integers, Cartesian product of the positive integers with itself, is denumerable since it is countable. So this is equinumerous to the positive integers. And so there is a bijective function g going from the Cartesian product of the positive integers with itself to the positive integers. And that's the beauty of the properties of being equinumerous. Since we know that the Cartesian product of the positive integers of itself, since we know that that's denumerable, we know that there is some bijection out there. But we don't need to know what that function actually looks like. We just know it's a bijection. And so consequently, the composition where we take G, compose F, going from the positive rational numbers to the positive integers is a one-to-one function. And here we're using the theorem we used earlier, namely theorem 525, which tells us that if we have a composition where both functions are one-to-one, then so is the composition. And so here we have G is one-to-one, since it is bijective, and we have proven that F is one-to-one. And so it is injective. So now the composition is one-to-one. And so we have by theorem 525. Now, we have a one-to-one function. Now we apply theorem 815. Since we have now a function from the positive rational numbers to the positive integers that is one-to-one, we get that the positive rational numbers are countable. So by theorem 815, the positive rational numbers are countable. But this is not quite what we want. We wanted to show that the rational numbers is countable. Well, the good thing is, this also tells us that the negative rational numbers are countable. Indeed, let's go ahead and let h be the function from the positive rational numbers to the negative rational numbers be defined by h of a over b is sent to negative a over b, where a over b, the input in the rational numbers, is chosen so that the GCD is 1, so that guarantees that we have a function. I leave it to you to verify that h is a bijection. H is a bijection. So that's a quick verification. And thus, the rational numbers, the positive rational numbers, is equinumerous to the negative rational numbers. So now we're going to use theorem 812 from last time, namely the second portion. If A and C are disjoint, and B and D are disjoint, and we have that A is equinumerous to B, C is equinumerous to D, then the union of A and C is equinumerous to the union of B with D. So now we have that since the positive rational numbers is equinumerous to the negative rational numbers, we get the following. So by theorem 813, so this is the one about that equinumerosity satisfies the properties from an equivalence relation, essentially. So we have reflexive, symmetric, transitive. So if we apply theorem 813, we get that the negative rational numbers is equinumerous to the negative integers. Since the positive integers is equinumerous to the positive rational numbers, as we just showed, and the positive rational number, the positive integers are equinumerous to the negative integers. So we get this statement. So by theorem 812, we get that the positive rational numbers union the negative rational numbers, and these two sets are disjoint. This is equinumerous to the positive integers union the negative integers. And all that we need to get the rational numbers is just 0. We just need to take the union with 0. So another application of theorem 812 yields that the rational numbers, which is equal to the positive rational numbers union the negative rational numbers union the set containing 0, is equinumerous to the positive integers union the negative integers union 0. But this is just the integers. And so we get that the rational numbers are equinumerous to the integers. Which shows that Q is the numerable. And we're done. We have now concluded the proof. And that's the key thing with equinumerosity in working in this manner. It is not that we have to actually find explicitly the function that gives us that Q is bijective to the positive integers, but the fact that equinumerous sets behave similar to equivalence relations allow us to use our prior knowledge of what those sets are equinumerous to then build the properties of what the corresponding set that we have is actually equinumerous to. And that's what we have done here. When we applied theorem 812 again, we were thinking about this as our set A, and our positive integers union negative integers as our set C, and both B and D were just a set containing the element 0. And taking the unions, we got back the rationals and the integers. And we got that these were equinumerous by the theorem. And so that's just the ideas to keep in mind, is that yes, to prove that two sets are equinumerous, we need to show a bijection. But if you know what one set is equinumerous to already, can you use those bijections that you get for free to then show that there is a bijection to the set that you want? And that's essentially what we have done in this case with Q. We did construct a function, and a function that we had a good grasp of, namely the function f. And from there, once we showed it was one-to-one, we were able to just deduce that the positive rational numbers were the numerable. And then we went from there and slowly built up to finally get that the whole rational numbers is the numerable. And so that finishes it off for today's lesson. Our next lesson is going to discuss two more topics that are from 8.1, and then we're going to start going into 8.2.